And there you go. All right, so on the screen, we've got a frictionless cart of mass M. We're being real creative. Mass is M. It's attached to a spring with a spring constant K. When the cart is displaced 6 centimeters from its rest position and released, it oscillates for a period of 2 seconds. So that's 6 centimeters. That's our what? What is that? Okay, I'm glad you're in my class now. That's the amplitude, right? That's how far you're displacing it from equilibrium. Okay, that's the amplitude. And as it moves back and forth, your period is 2 seconds. We've got 4 students discussing what's going on. So we've got 4 nerds sitting around looking at this, trying to figure out what's going on, and we've got opinions from each. So let me make sure I have my chat up so I can see what everybody says here. And Aiden is our first one, or Aden, it's misspelled Aiden, but since the spring is stretched more, because originally it was 6 centimeters and now it's 12, since the spring is stretched more, the force will be greater. So let's start there. So those playing along at home and those in the class, let's just say, do we agree that Aiden at first is correct? When we stretch the spring more, are we going to have more force? Y'all can be verbal. It's either yes or no. So it's really a 50-50 shot.
Yes.
Yes, because the force of a spring comes from what? How do we calculate force of a spring?
The spring constant times the displacement.
Spring constant times the displacement. So if we displace it more, doesn't that displacement get bigger? So then when we have the product of that times the constant, then we have a larger spring force. So far Aiden's on track, right? We have a greater spring force causing a greater acceleration. Yeah, if the net force goes greater in one direction, the acceleration of course is going to be more. And so if you've got more acceleration, the speed is going to be higher. Okay, so first sentence from Aiden, he's on point. Next, it says, since the cart is moving faster, the time will go down, meaning the time's going to be reduced. And he estimates probably to 1 second since the force is doubled. Do we still agree with Aiden?
No.
If it's faster, will it get the job done quicker?
Not in this case.
Why not in this case?
Because the formula for calculating the period, you take the mass and divide it by the spring constant. Well, we're not changing either of those, so the period won't
pause. Hang on a second. You are cheating because you've had this subject already. Everybody else. All right, I don't want to get too fast into this because everybody else is like, hold up, I think so, maybe. You covered this last semester, right? So
yeah,
you're right, but let's just take it one step at a time. What is Aiden not thinking about? It is going faster, but isn't it having to cover more ground? So it kind of cancels out a little bit. So Aiden's not accounting for the more ground that's covered. He's just like, hey, it's going faster, so it's gonna be done quicker, right? Okay, so let's see what else we have. Barb. I think no one's been named Barb for years. Okay, so Barb, somebody in here is probably named Barb. The cart has farther to go now. So Barb at least understands it's got further distance. And so she says, well, if it's got further to go, it's going to take longer to complete a cycle. So she's like, if it's got twice as far to go, it's going to take twice as long. So Barb understands the longer distance, but forgot about the speed variant. Aiden understood it's going to go faster, but didn't think about the length that was increased. So we kind of got, each one has a little bit good and a little bit, off-putting. And then Chuck comes along. So good old Charles says the cart has 4 times as much energy, and the conjugate variable for energy is time according to the Heisenberg uncertainty principle. And just as soon as I read that, I'm thinking this kid has watched too much Big Bang Theory and he's trying to flex on everybody, throw it out enough terms so they'll just assume he's right. The energy quadruples when the spring stretch is doubled, and so time must be only 1/4 as much. The period will only be 1/2 second. So if we don't know, we might want to set Charles aside and just say, maybe, I'm not sure. Or we can just say, look, this guy's kind of he's just flexing with a bunch of words, whatever, let's put him aside. Let's see what Dallas has to say. Now, if Dallas is anything like the football team, automatically we can say that he's not going to be in the playoffs. But let's see what he has to say about physics. Stretching the spring twice as far means that K is twice as big. Let's stop there. Do we agree with Dallas? Students that have not had simple harmonic motion this last semester. If you stretch a spring twice as much, I'm not talking about you got a slinky and you stretched it till it was damaged. Now I'm talking about that. You just got a spring, you're in its normal ability of range. If you double the distance that you stretch it, have you doubled the K?
Isn't K a constant?
Yeah,
especially
I
if
know, right? Why isn't
no,
anybody else putting that? Why are you the only one? A K is a constant. What does a constant mean?
doesn't change.
Doesn't change. So Dallas is already full of crap, right? You're not going to get a K twice as big just because it was stretched. It's a constant. What does a constant mean? It means it doesn't change. And then he goes on to say, then the period is 2 pi times, okay, well, the period is 2 pi times the square root. But then it says of the, let's see, spring constant divided by the mass. Is it the spring constant divided by the mass? It's mass divided by spring constant. So Dallas is not only doesn't understand what a constant is, he's getting his formula wrong. So Dallas is trash as well. Now, if we look at this, we can say we really don't agree with any of these. So what could we say? Now let's go back to our esteemed colleague from the west side of Frisco. Tell us, why is it that it's not, the period's not going to change?
Because even if you stretch, like if in terms of the formula, right? Like it's square root m over k. There's no distance in the formula. So regardless of how much you change the distance, the period's not going to change.
There you go. That's exactly right. When you look at the period of a, what was this, a spring, it's 2 pi. Okay, well, that's 2 times 3.14. All right, that's not a variable of anything. It just is what it is. Times the square root of, okay, that's a math function. And then we said it was what, m over k, that's mass over a constant. The only thing that can really change here is the mass. If you change the mass, the period would change. Or if you changed out the physical spring, you'd get a new spring constant and it would have a different period. But stretching it out further or less, that's just going to change the amplitude, which would change the velocity as it goes through equilibrium. But the overall period, the time it takes to make one full oscillation, is the same. May not make sense if you reason out, you're like, dang, I think that's going to make a difference because it's got to go twice as far. Just look at the formula. Consider the formula and see, does that factor change? It doesn't, or it's not even put in. The amplitude is not in that formula. All right, so that got us through our warm-up. Let's open up your homework from last class. I'm going to switch the screen over to that. And let's see, I know in my class, I walked you guys through what, 4A. I don't know that everybody got the same treatment. And I think someone asked me about something in here. Let me scroll back through the chat. 6, 7. All right, I didn't understand number 3. All right, so I'm going to start with 3, and I've got a request for 3. All right, I see 3, 6, 7, 8. 3, 6, 7, 8. All right, if anything else pops up along the way, slow me down and keep me concentrating on that. Let me get it in front of me so I know what I'm doing, and we'll go through that. You guys did that, yes? Ish. Okay. Do we want to do anything before number 3, number 1 or 2? We okay with those? Did you do it for classwork? Did you go through the whole thing? Oh, well, then you guys are going to just let it just go over your head. You can start working on today's page. If you don't need any of this, I gave it to them for homework. So I'm going to work through number 9 with them, and then I'm going to let them start working on the homework. So if you're good with this entire 2-page packet, look in today's Canvas and look at, it has the warm up that we just did. And then it has the homework that has, I think it's like 4 pages, but it's kind of spread out. It moves pretty fast. Focus on that today. If you have questions about it as you go, let me know. I've got it worked up here. All right, so we have, I'm going to go to question 3 on the screen. All right, this says when an acrobat swinging on a trapeze reaches the equilibrium position, the net force acting along the direction of motion is 0, because that force is the restoring force. When you're at equilibrium, the restoring force has gone to 0. Think of like a pendulum. This is just like a pendulum. Why then does the acrobat swing past the equilibrium position? Well, the acrobat has a velocity that is increasing. The speed is increasing as it approaches equilibrium because the acceleration is pointing towards equilibrium. So if the swing is going towards that point and it hits that point, so let me just draw it. We've got, all right, there's my acrobat, and they're going this way. All right, as they get to that equilibrium position, we can say, hey, we're at equilibrium right here. Yes, force has equaled to 0, acceleration is equal to 0, but velocity is equal to its maximum. It's been speeding up until it gets to this point. Then it's released of all acceleration, but it still has speed. If you've ever been in a car, driving a car, and you just let go of the gas pedal and you just coast, just because you get off the gas doesn't mean you're going to stop. Okay, so you're going to be going through equilibrium at that maximum speed. Once you pass equilibrium, the acceleration points at equilibrium. So once you pass equilibrium, the acceleration changes direction and you're going to start slowing down. That's why as the swing goes up, it starts slowing down, changes direction, heads back towards equilibrium. Your maximum velocity occurs at equilibrium. And that's why you're not going to stop there. You're moving. All right, let's see, 2B, how tangential acceleration decreases. All right, so someone asked about 2B. How does the magnitude of tangential acceleration along this change? And then wondering how it decreases. Okay, well, a tangential acceleration is influenced by the restoring force. The restoring force is drawing you towards the equilibrium. As you approach equilibrium, that restoring force is reducing because you're getting closer. And therefore, if the force is reducing, the acceleration is also reducing. Now, it is still an acceleration, therefore the velocity is getting bigger. It's still a positive acceleration. The acceleration doesn't change direction until you cross equilibrium. Okay, that gets us through. I'm just covering things that are popping up in chat. So that was 2B and number 3. Let's see. Was there any question about 4 or 5 in that we needed to review before going to the second page? 4 or 5. I can look back in the chat and see if there was a 4 or 5 in here. And I see 6 and 7. I see 3, 6. Sorry, not to, oh yeah, someone said I was off by 0.002 for some answers. Is that okay? Absolutely. That just shows it's rounding error somewhere. I would not be worried about that in the least, not in the least. Okay, so I don't see anybody requesting 4 or 5. Let's flip over to 6. I know someone asked about 6 within the chat, so let's take a look at this. One thing that we're going to have to do in number 6 is we're going to have to define what little g is. We know little g on Earth, we've been using 10, but we've taken this clock and the problem and it's been relocated to the moon. Well, the moon has a different gravity, acceleration of gravity than Earth does. So we've got to go back and we've got to calculate it, what it is for the moon. In order to calculate it, let's not forget our formula where we've got g, little g's acceleration of gravity is equal to big G. That's the constant, 6.67 times 10 to the minus 11. It's on formula charts, it's easy to find. Times the mass of that planet divided by the planet's radius squared, or your distance from the center of that planet. When we do that for the moon, I was able to calculate with my math as g is equal to 1.62 meters per second square. That's little g on the moon. Now we can take it into our formula, and remember our formula is the period is equal to 2 pi square root of L over G. We have a new G, instead of using 10 there, now we're going to take this 1.62 and we're going to plug it into that G. When we do that, we're calculating the period. We don't have to rearrange this equation at all. It's 2 times 3.14. Use 3.14 for pi, so we can all kind of get similar numbers instead of using the button on your calculator. In this case, I was able to solve this and say t is equal to 2.47 seconds. That was from, that's my little g that I solved using g times m over r squared for the moon. Now that I see that my period on the moon is 2.47, in the previous problem number 5, it told me the period for the on the Earth was 1 second. Well, if it's 2.47 seconds on the moon, that means it's slower on the moon than it is on the Earth because it takes 2.5 times as long. What would the length be? The radius? No, the length is going to be the same length for the clock in number 5. So length is still, you're designing a pendulum clock on the Earth to have a period of how long should, whatever you get for number 5, that's going to be the length that you're going to use. Because it said it's the same clock, right? So if I go back to mine, I was number 5, I was able to determine 0.25 meters equals my length. On number 6, the radius, the radius here, this is the radius for the moon, not the length of the pendulum. I mean, that'd be a really long pendulum. Yeah, so yeah, you have to see that because it says take the clock from the above problem. It's one of those tricks. If you look past that and you're looking just the numbers, you've lost some information and you wouldn't be able to complete this problem without seeing that. All right, if we're okay with 6, I'm going to watch for and listen for anything. I'm going to bump down to 7. I know the question that I saw was for 7B, but I want to touch on 7A because we're going to use information from 7A to do 7B. You kind of have to get the first one right to get the second one right. Okay, I'm going to do the same thing. We don't want to give up on our guess method. How did I get 1.62 again? 1.62 right here. I calculated little g for the moon. I said big G, which is the gravitational constant, 6.67. You write that on the side. Big G is equal to 6.67 times 10 to the minus 11. The mass of the moon is equal to 7.35 times 10 to the 22nd. And then the radius of the moon equals 1.738 times 10 to the, is that times 10 to, is it, I think it's a 6. I can't tell, I've already written over it, so it's hard to read. But I used those components into the little g, the acceleration of gravity equation. Remember, gm over r squared. When we did the force of gravity, we did gmm over r squared. Because to go from an acceleration to a force, you just add another mass or multiply it in another mass. So by doing gm over r squared, in the margin there, I have my g, my m, and my r. I was able to calculate the acceleration of gravity for the moon. Let's see, when I did number 6, I already knew that the moon's gravity was 1/6 the Earth's. That's good. So I didn't calculate for the moon's g. Is that fine, or should I calculate? You know, if you're doing the work for points, I would calculate it just to make sure that you're getting a value and you can show work. If you're doing something to say, will it be faster or slower? All you really need is an estimate. So in this case, knowing that it's 1/6 is good. But what if I gave you points for getting this and showing the work and points, and I could say, well, you just wrote down that it was a 6, but you didn't show me that you knew how to calculate little g, then you might run into something. So I think what you did for homework is fine, as long as you knew how to do the process. Because what if I said it was one of Mars's moons? Then you're like, oh, well, I don't know what the comparison is there, and I forgot how to calculate it. I want to make sure you know how to calculate it. Let's look at number 7. When the mass of a 25 grams is attached, okay, right away, I need to make an adjustment. We don't work in grams, we work in kilograms. So off to the side, I'm gonna say mass is equal to 0.025. That's right, 1, 2, yeah, kilograms. Is attached to a certain spring. It makes 20 complete vibrations in 4 seconds. 20 vibrations. A vibration would be like a cycle, right? You know, vibrate, it's a cycle. How do you know what the length of the string was for number 6 again? Go to number 5. Your answer for number 5 told you the length of the string. So you solve for that number 5, and then number 6 was a continuation. On number 7, what is the period of this for number 7? How do we calculate the period?
Over 20.
2 pi.
Well, they tell us it's 20 vibrations in 4 seconds.
The period is time over number of vibrations.
Right. So, well, if a period is how long per vibration, then like you said, it's time, it's seconds per vibration, of seconds per cycle. So it would be 4 divided by 20, which should be what, 1/5 or 0.2? 0.2. I'm just basically reading through the question and trying to pull in the my given off to the side of the margin, and they tell me 20 vibrations in 4 seconds. What they're trying to do is tell me the period, and we just have to make the quick calculation. Now here it says, what is the spring constant of the spring? So we need to calculate that. Now that's what we can use the period formula to calculate the spring constant, because we're looking for the constant. So K equals question mark, and we know that TS equals 2 times pi times the square root of M over K.
Wait, wouldn't T equal 5? Because I thought that you would divide 20 by 4 seconds to equal 5.
So a period is how long does it take to do one vibration, right? So that would be vibrations per second.
Okay.
Oh, no, sorry, seconds per vibration. It's how long does it take to do one vibration? So that's seconds per vibration. That's seconds over vibration. Right. So that's, yeah, because the reverse would be the frequency.
Oh, okay.
That's how long to do one. Now, if we want to, we need to rearrange this equation, because what if we're not using numbers? We want to solve this equation for K. So if I divide 2 pi to the other side, I'm going to drop that subscript S because it's going to make it messy in my handwriting. I'm just going to keep it as T divided by 2 pi is equal to the square root of M over K. Then if I square both sides, I would get T squared divided by 4 times pi squared is equal to M over K. If I'm doing this the long way for anybody that sometimes gets math challenged, the easy way to continue to solve this, when you have a fraction equal to a fraction, you can cross multiply, and that's a valid thing to do. So T squared times K, I'm going to move this up here. I would have T squared times K is equal to 4 times pi squared times M. Divide both sides by T squared. K equals 4 times pi squared times M over T squared. Make sure you can see that square. So that's how we would solve for K. It's a simple rearrangement of the formula. If this is our exam in May, when we're going to do very little math and more identifying and resolving formulas so that we solve for a certain variable, we would be done. But we're not, because we've got numbers. Let's go ahead and plug in our numbers. We've got K then would be equal to 4 times 3.14 squared times mass 0.025 divided by T, which is 0.2 squared. So then K equals, all right, let me grab my handy little calculator here. 4 times 3.14 squared times 0.025 equals, divided by 0.2 squared equals. Now I get K is equal to 24.649, so I'm gonna call it 24.65. And look, my answer is really close to theirs. Rounding error, whatever. Good enough for me. Plus, I'm pretty confident I've done this 3 times today and I got the same answer, so I think I'm right. Now we get to 7B, where a lot of the questions start to come about. If allowed to come to rest. So we've got an object, a mass on a spring. And let's say that it's a vertical spring. So when it comes to rest, that will cause the spring, it will be stretched from equilibrium. If this was a horizontal spring, the spring really won't rest until it is at equilibrium, or the friction from the object, the mass, resists the movement back to the equilibrium position. Let me just take a look at this. 4 over 20 or 0.2. Right, 4 over 20 is 0.2. So yeah, I don't like 4 over 20 because you can clean that up. You could say 1/5 or 0.2. So make sure you're bringing your fractions to, you're cleaning up your fractions. Decimals are always better. All right, so now like I was saying, you really don't, you'd have to know more information about like the friction and all that to determine on a horizontal spring, when would the spring's restoring force not be able to overcome the friction or whatever. So let's assume for this problem, this is a vertical spring. Okay, I've had that question all day long. Well, how do you know it's vertical? It just makes more sense. For the information we have, it makes more sense. So let's draw a picture. All right, we've got a vertical spring. There it is. And there's our mass. Okay. It's chill. It's happy. It's not moving. If it's not moving, that means its velocity is 0. And it's still 0. Wait, still 0, right? So that means it's got a constant velocity. Constant velocity of 0. We remember back from Newton's laws when we did forces, a constant velocity means balanced forces, right? What forces are acting on this? Y'all talk to me. What forces are acting?
Force of gravity.
Force of gravity. All right, that's going down. All right. What's balancing that force of gravity?
Force of the spring.
All right, force of spring going up. So we've said that they are balanced. So force of spring equals force of gravity. How do I calculate the force of gravity?
Mass times gravity. Mass times
Mass times gravity, mg. How do I calculate the force of a spring?
It should be equal to force of gravity.
Right, but what if I don't know force of gravity? How do I, generically speaking, how do I calculate the force of the spring?
The spring constant times the displacement.
Yeah, k times x. K times x. Now, we said force of spring and force of gravity are equal to each other. So that means mg is equal to kx. Okay, cool. Mg is equal to kx. We want to solve for x, so we're going to divide k over. And we're going to say that mg divided by k is equal to x, because those cancel out. Now we can start to solve our problem. The mass, we know that it's written over on our margin, is 0.025 divided by, times 10. Can't forget gravity. Divided by the spring constant. We calculated that in the last problem, 24.65. That's equal to x. Now I'm gonna grab my calculator. 0.025 times 10 would be 0.25 divided by 24.65 equals, here I get x is equal to 0.0101419878. All right, that's what my calculator's telling me. Now, why is my answer so much different than theirs?
Because you use 10 instead of 9.8.
No, my answer is really different. They have 0.993 and I have 0.0101. You know, why is my
That
why is
answer
it so
is
different?
centimeters, and your answer is in meters.
Exactly right. Our formulas use meters. And if you want to use centimeters, you got to bump that over 2 times, multiply by 100. And I have x is equal to 1.01 centimeters. They have 0.993. I mean, we're within millimeters of each other. We're good. So when you're looking at the solutions that they have listed and you're comparing it to your own, just be aware that they're showing it in centimeters. It's a cleaner answer in centimeters, right? 1 centimeter is better than 0.010 meters. And it's a little bit easier than saying, well, it's 1.01 times 10 to the negative 2 meters. Should we always assume the spring is vertical unless specified? I hate to say that I always assume. I look at the problem and see which, if it doesn't tell me, and it usually will, but if it doesn't tell you, that means one way or the other will make more sense. Like it's going to be logical that they would set this problem up to be vertical compared to horizontal. It just makes more sense because I said, hey, it was allowed to come to a rest and the spring was stretched. Well, what would cause the spring to stretch? That weight bearing down on it. So what is the difference between amplitude and displacement? Well, amplitude is the maximum displacement from equilibrium. Just simple displacement can be, okay, what if we stopped the weight at any given time? It could be a little bit away, a little bit, you could be halfway between equilibrium and the amplitude. So amplitude is that furthest point, but displacement is any point along the way. So displacement is any point in its range where amplitude is the furthest point in its range.
Mr. Watley,
Yeah, what's up?
are we commonly going to see problems like this where we have to recall like drawing a free body diagram and
Yes.
finding force of gravity and stuff like that?
Yes. And you're going to get a ton of practice of that. When we finish this unit next week, we're going to go into rotation. We'll spend extra time in rotation, and rotation is going to pull back in energy. It's going to pull back in kinematics. It's going to pull back in a lot of things. So you're going to be reliving this stuff all over again. After that, rotation is our last topic. and we're going to go into review. And review is going to be a lot of FRQ reviews, bringing up problems that we haven't done in a long time, because the questions you're going to see on your FRQ in May is going to be like a single question that pulls in information from like 3 units. And you need to be able to tie all that in together. So the practice is going to be good, and it's going to be based on just the experience you have in looking at these problems. And it's one thing if you're like, oh, I get it, no, I don't have to do these problems. Doing the work is what's going to help you recall this information when you're under pressure taking that test. Let's see. Will the AP exam also have multiple choice questions, or will it be just FRQ? It's going to be mixed. It's going to be a tradition. As of today, it's still going to be a 2-part exam where you have multiple choice and you have FRQ, and you'll have to take it in person as long as the school is open. And with all the treatments coming out between we have 3 companies now, between Moderna, Pfizer, and then I think there's a 3rd company. It's looking like things are going to be better and better by the time we get to May. Let's see. I think.
One question about
Uh-huh.
on 7A.
Yes.
The answer is 24.6. Would that be around 2.467?
I got 24.65 was the answer I got.
Okay, it's just I did the math on my own. I thought 2.467. Am I supposed to convert units?
You did have to convert units with your grams to kilograms. So do you have the mass as 0.025?
Yeah.
Okay. All right, now look where I solve for K. I'm gonna put a little arrow right here. When I solve for K, I have 4 times pi squared times mass divided by the period squared. Because I freshly put it in my calculator as I'm doing it here, and I was able to get the answer that I calculated 24.65 based on what's on the screen. And let me move that docking panel out of the way so you can see the whole screen. Let's see if I put it there. Because I even have the numbers on the screen now where you can see where it came from. Did you, your denominator, did you square it, 0.2 squared at the bottom?
Yeah, but that's, wait. I think that might be. Okay, yeah, no. Yeah, I think that's very high.
All right, let's roll up to 8. 8 is where we start using that 3rd equation I gave you guys. That 3rd equation, I'll probably have it memorized now from today. It's like we have what x, which is the position at any given point in time, is equal to the amplitude times cosine. And remember, we're using radians, radian mode in your calculator for this cosine because of the next step, which is 2 times pi. When you include pi with sine or cosine, it's got to be in radians. Now we're going to multiply by the frequency times the time. That's the equation we're going to use for all these problems. And I'll set up 8A, and it should help us give it a really clear idea of how to do B, C, and D. They did list the answers of B and D as 0. And that is because once you get your answer, it's such a small answer that they got. They just said, well, if it's 0.0, I'm just going to call it 0. All right. I still got an answer for each. So let's walk through these and talk about them. All right, we have a mass on an air track attached to a spring completes 1 oscillation every 2.4 seconds. All right, so they told us the period equals 2.4 seconds. Well, my formula doesn't have period, it has frequency. And I know frequency is equal to the inverse of the period. So that's equal to 1 over 2.4. Now you have a choice. You can use 1 over 2.4 in your formula. And if you do, you'll get either the same or very similar answer than they do. If instead you put into your calculator 1 divided by 2.4, you get 0.4166666667. So you're like, hey, I'm just going to go ahead and say that that is about 0.42. Well, you've just rounded here, and that's going to cause your answers to change from what's on the screen. They'll be close, but they'll be different. So I just want to let you know, if you round right now, you're going to start deviating from their solutions. So for the most part, I'm going to persuade you to encourage you to not round until the very end. When you get your final solution, then round, okay? If you're using the 0.42 and you did, that's fine. The mechanism, the function, that's what's more important here. But just know your answer is going to vary a little bit. Also, if you get a negative number for your position, that just means you're on the left side of the equilibrium. Doesn't make you wrong, you're on the left side. If you get a positive number, you're on the right side. Let's set up the problem. Let's see, is there anything else? Oh, it says that it was released from rest a distance of 0.1 meters from equilibrium. What kind of variable is that? What are they telling you there?
Amplitude.
Amplitude, yeah. All right, so we got amplitude is equal to 0.1 meters. Awesome, let's plug in the things we know for A in that equation. We don't have to rearrange the equation, it's already solved for X. Perfect, that's what we need it solved for. X is equal to, we said the amplitude is 0.1 times the cosine, 2 times, I want you to use 3.14 for pi, times the frequency, 1 over 2.4, times the time. They gave us a time of 0.30 seconds. All right, so X equals 0.1 times cosine of, let's plug this stuff in. All right, 1 divided by 2.4, let's get that going, times 0.3 times 2 times 3.14. I get 0.785. 0.785, nice clean number. Now I'm gonna take the cosine of that, but first I'm gonna check my mode in my calculator, confirm it's in radian. And then I'm gonna click cosine of my 0.785, enter, and then multiply by 0.1 times 0.1. And what I get is X is equal to 0.0707, on and on and on. Now, this is in meters. Their answer is in centimeters, so I would just simply multiply by 100. X is equal to 7.07 centimeters. That's the same thing they got. It's a little bit of a beast to do the first time. The good thing is you've got 4 chances here, and you're going to do the exact same thing. The only thing you're going to do is you're going to take this last number and you're going to exchange it with each one of these. I'll tell you the solutions that I got using this exact same setup. For B, I got 0.00796 centimeters. See, it's really, really small. And I just kept it in centimeters because that's what they were doing. For C, I got 7.10, similar to theirs, but different. And for D, I got 0.04. Again, if on one of these you got a negative, that just means you probably were using that 0.42 for the frequency instead of 1 over 2.4. You rounded there, and it just caused that rounding error, made you go from barely to the right of the equilibrium to barely to the left of the equilibrium. I plugged in your first equation on the calculator and I got 7.03. Is that right? Yeah, you must have rounded something along the way. Let me tell you exactly what I typed into my calculator. 1 divided by 2.4, enter. I did that fraction first. Then I said times 0.3 times 2 times 3.14, enter. That gave me a value of 0.785. Look and see if you got the 0.785 at that step or if there was a change along the way. I hit my cosine button and I pointed at that solution of 0.075, hit enter, then I said times 0.1, enter, and that's the solution that I was able to get. We're both very close. Am I worried about it if you're that close? No, heck no. As long as your function looks correctly and you're nearly there, that's what I care about. And again, the exam in May is just about setting it up. It's not about calculating it. Why would we convert 0.1 meters to kilometers? 0.1 meters would be 0.0001 kilometers. We do all of our, don't forget, we use kilograms for mass. We use meters for length. The only one we use kilo for by default is mass. That gets a kilogram, but distance has always been in meters. Okay, if we need to come back to this one, make sure you get my attention. Number 9 is similar but different. Okay, it's similar because we're going to use the same formula. It's different because now they're giving us the position and we have to then determine the time. So it's still x is equal to a times the cosine of 2 times pi times frequency times time. All right, in this case, what do they tell us in the problem above? What is the first time? Oh, so it's still based on the problem above. So we know the amplitude is equal to 0.1 meters. We know that the frequency is still equal to, oh gosh, what was it? See if I can find it in my notes. 1 over 2.4, 1 over 2.4. And let's see, is there anything else pertinent? No. And now they're saying, what time will you arrive at position negative 5.0 centimeters? Well, we don't use centimeters, we use meters. So we need to, okay, I'm caught up there. We need to convert this to meters. If we're going to convert this to meters, that means that the position is x is really equal to negative 0.05 meters because we don't do centimeters. I'm going to go ahead and just plug the numbers in and we'll start to rearrange and look at this. This is a problem that a lot of people were able to do really well until they got halfway through and then they hit a stopping point and they're like, okay, I'm not sure what to do next. Let's take it one step at a time. All right, if x is negative 0.05 is equal to amplitude of 0.1 times the cosine. In the parentheses, I have 2 times 3.14, because pi is 3.14, times the frequency, which is 1 over 2.4, times the time. I'm looking for time. How about for a first step, let's multiply the numbers that we know inside the parentheses, just as a one-step cleanup. So let's just repeat all this stuff. All right, now I'm gonna get my calculator out just because I do better with it. I have that 1 divided by 2.4 times 2 times 3.14. All right, so that gives me 2.62 t in the parentheses. So I have negative 0.05 is equal to 0.1 times cosine of 2.62 t. I want to divide both sides by this 0.1 to kind of clean that up. So on this side, I'm going to divide by 0.1. On this side, by 0.1. So negative 0.05 divided by 0.1 equals negative 0.5 is equal to cosine, because these cancel, 2.62 t. Now for me, the next best step would be to multiply both sides by the reverse cosine, the inverse cosine, so that I can move cosine to the left side. So if both sides, if I use the reverse cosine, I can say that cosine negative 1 on the left times negative 0.5 is equal to 2.62 t. In order to use that reverse cosine function on my calculator, I'm using a scientific calculator, and you either hit second or shift and then the cosine button. I've got a TI-84. I'm going to hit second in the top left corner, then the cosine button, and then negative 0.5. That is 2.09 is equal to 2.62 t. I'm going to divide my 2.09 divided by 2.62, and I get 0.7977. That rounds to 0.8 seconds equals my time. So at 0.8 seconds, my object will arrive at the location of 5 centimeters away from the equilibrium on the left side. It's a little bit mathy, you know, if you like algebra, if you're good at it, you can skip some steps and combine steps. Yes, I get it. I went slow and did individual steps for those that understand the concepts better, but have to take their time with the math. And I want to make sure you can see that. All right, take a look at that. Let me know if you've had any questions. That's the last problem from our homework from last class. See, I don't see anything popping up. Let's do this. Let's take a look at where we are in Canvas. So what we did is we reviewed the practice from last class. We started with the warm up. What I want you guys to do